So viral marketing in social networks. So this is also popularly known as influence maximization through networks. So how many of you are aware of this topic, influence maximization through networks? Information propagation through networks, actually, yeah. So like how gossip spread, right? How, I mean, gossip, or it can be positive information about a product or something like that. So in the algorithmic sense.
In one of our days at the Winter Studio, we discussed about, for example, if we have a telecom network, and let's say one of the person is leaving the network to go for another telecom service.
Churning, yeah.
How that influence spreads among neighbors.
Okay, that is like for one particular node, the influence of that in the network when churning happens. But this is like in the given entire network. In an optimal sense, how do you select, let's say, some small subset of individuals as your trendsetters, or the initial starting points where you feed in the information to them? They help you in maximizing the spread of information through networks. That's what it is. Okay, so good that this topic will be useful for you. So this is like very like extensively studied problem in network science and in general social networks. So I'll explain. There are multiple variants of this problem. So let me get started with the very simple scenario: viral marketing through single product. Right? Then we will get into the more complicated scenarios of viral marketing with extensions, and another scenario, viral marketing with product cross sell, in which I explicitly worked on that topic, and I'll summarize. So let me get started with the simplest scenario, viral marketing with single product. So these are all like some representative papers from. This is like the classical paper, and these are some of my own works. Yeah. So what is viral marketing? Let me first explain, and then explain the models, right, to capture the viral marketing thing. So I'll give my favorite example. So what is viral marketing? There is a network, okay, network of individuals connected with each other and so on. And there is some information which you want to spread through the network, right? Spread in the sense that you don't have sufficient time or resource to approach each and every individual and say that, okay, this is the product that I'm a company, let's say, this is the new product I'm launching, please try to buy this, right? My potential customers are like a few thousands, I cannot go, right? So for example, Amazon, Walmart, any of these product organizations, when they release new products, they can't approach or effort to send dedicated messages or emails or calls to their potential customers. Rather, what they do is they identify a small number of so-called targeted customers and give them sufficient information to buy the product. So sufficient discounts. In the worst case, they offer the product for free to them, and so that they ensure that these selected K people buy that product. And once they buy, these are like influential people. How do you select these people? That is the problem. But assume that you have a black box which takes network as input and it selects the top K influential people. What happens after that, I am trying to explain you. So if you give the free samples or sufficient discount over that product to these K people, they buy the product because they are influential people. Otherwise, they won't be in the solution set, right? By using your algorithm. So because they are very influential, they try out the product. If they like the product, they try to influence their neighbors. They are expected to be high influencers, right? So they try to influence their one-hop neighbors. So some of them may get impacted by their recommendations, and they also try to buy the product. And right, so initially these influential people are buying the product. Next, due to their influence, right, people in their one-hop neighborhood try to buy this product. So these are the initial influential nodes, right? 1, 2, 3, up to K. So because of their influence, some of their one-hop neighborhood people try to buy that actually. So this is their one-hop. Because their one-hop neighborhood people, some of them buy it, right? Not everybody. So some of them buy that and they try to influence their one half neighborhood actually. So one half neighborhood of these people, and these people will become two half neighborhood for the initial influential people, right? So some of the two half neighborhood people buy the product and they in turn can influence their one half neighborhood people, which becomes like three half people from the initial starting point, right? So this process goes, right? After some time, even if some people in this three half buy it and try to influence their neighborhood, they may not buy anything, then the influence propagation process stops, right? Or in other words, more technical terms, the random process dies out. Okay, so now the question is, okay, so the setting is, initially I am manually influencing these k people by giving either the product for free or sufficient discounts, so that I ensure that all these k people buy the product and I am going to influence. I meaning that I am the company which who I mean and I am introducing a product p into the market, right? That is the setting. So I am influencing these k people as a company manually, and these k people on my behalf are trying to influence some other set of people here, right? Here some set of people I'll get, and these one half people to these influential people in turn influence their one half people, and here is another set of people who buy the product, and so on and so forth. Sum of all these numbers, right? That is called the influence effect of these k people. We want to, so now the problem is we want to choose the k people in such a way that the sum of these numbers should be as maximum as possible. That is the problem actually. So one favorite example I would like to give is classroom setting. It's a very stylized example, I mean not stylized, very special example wherein the distance is one half. Classroom example, teacher. So teacher's recommendations are highly valuable and influential to the students, right? It's like a well-known thing. So students sit in the class. So teacher comes and if the teacher says that this book is extremely valuable for this subject, I am going to follow, something like that, then majority of the students buy the product. And now you see, if you if you are aware of this thing, many times teachers or faculty get complimentary copies from the publishers. So complimentary copies are no charge, they are not chargeable. The publishers give those books for free to the faculty with the hope that these faculty members go to the class and influence the students. So you see, the publishers are the I am the publisher, right? So I am going to bring in like a new book, right, into the market. This is my product. So this book I am going to give for free as complimentary copy to k teachers, k faculty members, with the hope that these k faculty members influence as many students as possible in the class, so that this sum of these things, so it's only one half thing, only this number count will be as big number as possible. So this is like a very special setting wherein the half distance is only one from the publisher point of view. But if you understand this thing, right, it's like generalization of this scenario in networks. And one another big difference is, in this classroom example I told, right, the role of teacher and the role of students is very clear. It's a hierarchical setting. Everybody knows the roles. He is the teacher and he is going to influence the students. In networks, right, these roles are not explicit. We don't know who is more influencer, whose values are more followed by other people. These roles are not known. We have to, or we may need to infer these roles and then look for the right or ideal influencers in the given network, right? So because of the absence of the roles in the network, and because of the absence of how much extent, right, one person can influence the other person, this problem becomes very hard and challenging problem, as opposed to the traditional classroom setting example I gave. Roles are clear, students and teachers, and influence is also very clear, this direction, student to teacher to student direction. All these things are explicit. In real life arbitrary social networks, Roles are not explicit, and the influence, level of influence among pair of individuals is also not explicit. That makes this problem very hard and interesting. Is this clear so far? Okay. So, and with this backdrop, right, so I will explain the mathematical formulation of this actually. So, propagation of influence is a probabilistic process, because if I am influenced, I might try to influence my neighbors. Suppose I have 10 friends, I might tell that, okay, this movie is excellent, I really enjoyed. If I tell like this to 10 of my friends, maybe 2 or 3 people saying that, oh, he told that movie is very good, this weekend I have free time, let me go and watch the movie. Maybe 3 or 4 out of those 10 people might watch the movie, which means that I am successful in influencing those 4 out of 10 people, right? That is what is my influential capability. So it's a probabilistic thing. Even though I am telling this to all 10 people, only 4 of them are getting influenced, right? There is a probabilistic thing behind scenes. So that's the reason it's a probabilistic process. And number of individuals in the network that are getting influenced by the initial trendsetters is an expected quantity. The initial K people are also called initial trendsetters or initial influencers that you have to identify. In the classroom setting, it is teacher, right? So, so now the problem is, I am just trying to define this bit more formally. So consider this marketing setting of a company introducing a product into the market, and we hope that it will be adopted by a large fraction of potential buyers, right? It's a buyer's network is available at our disposal. I am like Amazon or Walmart kind of organization, for instance. And with which set of individuals should we target for, right? The idea is to initially target a few influential individuals in the network who will recommend the product to their neighbors. So now a natural question would be how to find these initial influential people, right, of size K, right, so that they maximize the volume of the information cascade or the set of people, right. This is called information cascade. These influential people whom you select will in turn influence their one hop neighbors, and some of them may buy the product and try to influence their one hop neighbors, and so on and so forth. This is called cascading process. The volume of cascade is maximized. Volume meaning that those people who are successfully buying the product, right? That is the successful successfully influencing them, and this volume should be as maximum as possible for a given set of K individuals. Okay. So, how do you capture this propagation process? I mentioned the fact that influence propagation is a probabilistic process, right? How do you formally capture that? There are multiple models to capture this probabilistic process of information propagation. Linear thresholds model, independent cascade model, decreasing cascade model. Like that, there are several such models out there. But the top 2 are most important, actually, very, very popularly like considered for information to model the information propagation process as a probabilistic process. So, in the interest of time, I don't want to get into all these things, but I'll take one representative model so that you get a feel of how to model these things. Let me get started with the first one, linear thresholds model. So, I'll come back to this. I'll give an example first and come back to this. So, in linear threshold model, so how it works? Okay. So, it's a network setting. So, consider a particular individual, right, this circle, okay, and this individual has 5 neighbors, right, and this individual is influenced by each of these 5 individuals possibly differently, because some of the friends can be really like impactful in terms of influencing him, and some of them are not so impactful in terms of influencing him. So the percentage or the fraction of influence of the neighbors over this individual are mentioned here. So what this means? Okay, I'll just label this 1, 2, 3, 4, 5. So this is like person A of the focus here actually. So this person A is influenced by his friend, 5th friend, with probability 0.41, right? and person A is influenced by his first friend with the probability 0.12. It's like that. So his fifth friend is most influential for this individual A. Okay. So far these numbers are clear, right? And for person A, there is something called theta, which we called as threshold. So this threshold is 0.64, which means that exactly. So out roughly, if 64% of my neighborhood influences me, I will try to adapt that thing, whether it can be going to a movie or buying some product or something like that, right? So for instance, for me to buy the product or for me to go to movie and all, my threshold is 0.64, which means that if fifth individual and second individual influence me, then it is 0.41. What is the total influence? 0.41 plus 0.25, it is 0.666, which is greater than this theta. So if both fifth and second friend, second and fifth friend, I mean friends influence individual A, then individual A gets influenced. On the other hand, right, if A is influenced by first and fifth friends, right, A will not be influenced, right, because 0.41 plus 0.12, it is 0.53 only. So which is less than this threshold for person A to do any action, buying or going to movie or whatever. So A will not be influenced if 1 and 5 recommend a particular product to A. That's what it is. Yeah, you can think of, okay, let me put directions. These directions are like this. Yeah. A can also influence one, but the probability can be very different. It can be 0.49. You are right, yeah. Okay, so did you understand this point so far? So linear thresholds model, the name why linear came is because if a subset of my neighbors influence me, the linear is coming for the reason because I take some of their influential probabilities to check whether that is above my threshold actually, right? That's where the linear threshold model comes into picture, right? So that's what I'm exactly trying to explain. For some reason, if my fifth and second friends, right, buy the product, and any person can influence only after buying the product. That is the assumption, right? So fifth and second friends bought the product and they became active. Whenever somebody buys the product, we call it like active, otherwise inactive, just nomenclature. If they become active, they influence me, right? And that product, some of their influences scores is above the threshold, I become active, right? So this is called time period T1. At time T1, right, at a time T1, 2 and 5 are active. At a time T2, 2, 5 and person A is also like active. That's what it is, T2. So like this, now in time T3, all these three together try to influence their neighbors. That's how the set of active nodes expands. So this is what linear threshold model. So more formally, so these two slides I'm capturing. If you understand that, this is like simple mathematics. So for every node I, represent its set of neighbors as Ni, right? Node I is influenced by its neighbor J according to weight Wij, right? Sum of weights of all those Wij's is less than or equal to 1 in this case, right? It's normalized, right? Sum of this 0.41, 0.12, 0.25, 0.15, 0.07, if you sum it, it is 1. Or technically it is less than or equal to 1. So these are Wij's. So this is I, this is J, that kind of notation. So these Wij's, sum should be less than or equal to 1. This is just called normalization because I am saying that it's a probabilistic process, right? These are all like the weights, Wij's weights should be probabilities. For that reason, this normalization is required. Further, each node I chooses a threshold theta I uniformly at random from the interval 0 to 1. So for that center node 0.64, right? That is that particular node's threshold, which is like random, I mean uniformly at random picked from this interval 0, 1. So this threshold represents the weighted fraction of node i's neighbors that must become active, right, in order for node I to become active. And given a random choice of these thresholds, thetas, and these given a random choice of these thresholds, thetas, for every node, right, which is like a random process thing, right, an initial set s of active nodes, these two are given, thetas for all the nodes and the initial set of active nodes. I'll give both, right. The diffusion process propagates as follows. How? So in the given network, right, some of these nodes I make them active, green, and the remaining nodes are not active, they are not green. Now the question is, this is the network, some of them are active, some of them are not active. How the, and for every node I randomly select that theta. So this is theta 1, this is theta 2, this is theta 3. Given these thetas and initially active nodes, this is activated 1 and activated 2, these are the two activated nodes. So how the diffusion process proceeds? In time step t, all the nodes that were active in previous time step remain active. Whenever some node becomes active, it continues to be active in all the remaining subsequent time frames. We activate every node I for which the total weight of its active neighbors is at least theta I. So whatever I have shown, I just see whenever I am inactive, I will see at any particular time in period, right, sum of edge weights coming from the activated neighbors is above my threshold theta, right, in this case, right, it is this kind of scenario. I'll keep checking if that is the case. If so, right, sum of edge weights corresponding to activated neighbors is greater than theta I, then node I becomes activated. Otherwise node I doesn't become activated in that time period t. This process stops when there is no new active node in a particular interval. I'll repeat this random process from one time interval to the other interval as long as a new node, at least one node becomes active in a next time epoch. If at least one node becomes active, then I'll continue this. If at any particular time in period, in the next time period, if there is no new active node, I'll stop this. No point, right? Even if I continue, nothing becomes active, right? Following these equations. So this is called linear thresholds model. So the way information propagates, we are trying to model that using the by attaching probabilities to the edges and random threshold scores to the individuals. Don't think that this is the only way of modeling. This is a simple model of capturing how information propagates through the network. You can come up with your own more sophisticated model for information propagation. So linear thresholds model is one model. There is something called cascade model actually. What is this? There is one more, yeah, independent cascade model. It also has another similar definition. So I don't want to load you with all these different definitions, but it has its own definition like linear threshold model has here, right? So the purpose of all these models is just to capture how information moves from one stage to, one node to another node in a given network, right? So it's a random process actually, and the algorithms to detect the most influential k nodes should depend on this underlying model actually, right? So now we are defining the influential nodes problem more formally. We call it like top k nodes problem. So objective function, we call it like sigma, expected number of active nodes at the end of diffusion process. If you use linear thresholds model as the model to capture how information spreads from one node to the other node, right? So then sigma is called your objective function. So what is that? So far, suppose if you activate a set of nodes, right? Some I, j, k, something like that. Call all these nodes as S. All the nodes in S are activated. Sigma of S is nothing but expected number of active nodes at the end of diffusion process. What is this expected actually? Why, from where this is coming?
Because a node can active or not has a probability based on its neighbors.
Based on its neighbors, that's fine. But where is that expectation is coming from? It's the thetas are selected uniformly at random from 0 to 1. That's where the expectation is coming. So you have to run this process multiple times and take average. So in the first instantiation, for every node, the theta you randomly select from 0 to 1 interval. In first execution, for the first node, that value can be 0.45. In the second execution, for that node, theta can be 0.75. Third execution, it can be 0.45, 0.69 in another execution, like that. You fix the theta values for all the nodes in the first execution. For those fixed theta values, you calculate the spread if some nodes in S are activated. Now in the second execution, these thetas are like again sampled from 0 to 1 interval, and you fix the theta values for all the nodes, and for the same set S you calculate the activated nodes, right. So you repeat this process for multiple times and take average. That's where the expectation comes into picture, right. If S is the initial set of target nodes or initial set of nodes which I am making as active, for example ijk I am making active, this S I fix it. The influence of S I calculate by assigning these thresholds by taking uniformly at random multiple times, some 10 times or 20 times or 100 times depending on size of the network. Each time if S is my set of active nodes, how many other nodes S is making active actually, right. Due to S, how many other nodes are becoming active. In the first execution, how many of the new nodes are becoming active. Second execution, fix S only, right. Because thresholds are changing, the number of activated nodes can become different. Third execution, again, it can be different even though S is fixed. You repeat this for 100 times and take averages actually, right. So that will be the average number of nodes that the nodes in S can in expectation make active actually. That can be some 10.5 or 11.9, something like that actually, right. So S is the initial set of target nodes, then sigma S is the expected number of active nodes at the end of diffusion process. So for economic reasons, we want to limit the size of S, because I am a publisher, I can't give free copies of books to each and everybody, right? That is the economic thing. I can give free copies of books only to K faculty members or K teachers. So now my network may contain, let's say, some 1000 nodes or something like that. K can be, let's say, 4 or 5. So how can I choose those 4 or 5 most influential people with the hope that if I make them active, if I make those 5 as my S, right, in expectation they make as many other people as active as possible, right? That's the thing. So now this is the most important problem statement. For a given constant K, right, the K is coming due to budget constraints. The top K nodes problem seeks to find a subset of nodes of cardinality K that maximizes the expected value sigma of S. You understood this? I mean, don't worry about anything else actually. So you think linear thresholds model is the model using which you capture the information propagation. As I already told, linear thresholds model uniformly attaches a threshold for each node. So in the first execution, if there are 100 nodes in your network, for every node you randomly put some number in the interval 0 to 1 as thresholds. Edge weights are fixed, right? Only for the node thresholds, you randomly put some numbers in between 0 to 1 for all the 100 nodes. And initially, S is a set, so the cardinality of S should be K. Initially, you don't know anything, right? Nobody told you that these are the K nodes you should activate. Initially, S is empty, phi empty. Now, if there are 100 nodes in your network, each node can be a potential candidate to become active, right? So this is the brute force algorithm. So what it does is, initially your set of active nodes is empty. You repeat this for loop K times. If K is your set of active K nodes that you want to select, right? From the network, K most influential nodes you have to select. That is what is K. You repeat the for loop K times. Inside for loop, very simple. Looks very simple, but lot of computation is there in this. 2 lines. The first line is choose a node Ni. Initially it is empty. If there are 100 nodes, each one of those 100 nodes is a potential candidate. Take the first node, right? So then for that node, put it in the set A. If I make one active, what is the expected value of sigma of A. Now, if A, I will keep the second node. If I keep second node as active, what is its expected activation thing? Repeat this process for all the 100 nodes. Then how do you select the top first node in your actual activation? For each of these 100 nodes, this sigma 1, sigma first node, sigma of second node, right, sigma of third node, etc., sigma of 100th node you calculate. For whichever node that sigma value is highest, right, take that node and you activate it. That's what. The maximizing thing. Which of these 100 nodes has the maximum of this sigma value? Sigma is nothing but expected number of active nodes following, let's say, linear thresholds model. You take that node, put it into the solution set. So we have completed only one iteration and we selected only one node. So that node will, suppose node 20. So initially in the first just before first iteration, my set is empty. After the end of first iteration, my set A has one activated node 20. Now I'll repeat, right? I'll get into the second loop, right, in A2. So along with 20, I have to activate some other node. I have to figure out in the second loop, I have to figure out what is the second slot, which candidate I should keep into the second slot. So at the back of mind, just run this thing. There are 100 nodes, I told, right? 20th node is selected. How many possibilities are there for the second slot? 99 possibilities are there. Except node 20, all the remaining nodes are the potential candidates to fill this slot. So how can I know? Try with everything. So take the first node. So now your potential set will be A2 tilde. This is not the solution, you are calculating. In the second slot, along with 20, if I make 1 as active, 20 and 1, if they are activated, what is my sigma of A2 tilde? I calculate. Similarly, if my A2 tilde can be 20 comma 2, second node. Why only first node? It can be second node also, right? If 20 and 2 are my two activated nodes, what is the sigma of A2 tilde? So I repeat this process by, so 20 is fixed. For the second slot, I put 1, 2, 3, dot, 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 9, 18, 19, 20 is over, right? Then 21, 22, 100. For all these 99 potential candidates, I'll calculate this sigma of A2 tilde for whichever combination it is highest. I'll take that combination and fill that slot. Suppose it can be some for 39th node, that value is high, I'll fill that value with 39. So I completed my second round. So by the end of second round, I got 2 activated nodes. I repeat this process until I get all k nodes. It's a computationally very intensive thing, because for every potential combination you have to do this calculation, right? What is this sigma of activated set of nodes? You have to repeat that is like a expectation, and you have to repeat that experiment multiple times and take averages, right? And you are repeating this for all k rounds also. Only for 100 nodes itself is a significant calculation, but do you think only 100 nodes or 1000 nodes would be there in social networks? In real life social networks, millions and billions of nodes would be there. This calculation becomes very computationally expensive. Okay, so even though this algorithm looks very simple, this is greedy algorithm. It's a polynomial time algorithm only. If the network size increases, it becomes very hard problem. So this greedy algorithm is proposed in 2003 KDD paper, and its running time is big O of KNRM. K is the number of nodes you have to select as influential nodes. N is the number of nodes in the network. R is the M is the number of edges in the network. R is the number of times you have to repeat to calculate the expectation. It's a polynomial time algorithm, but explodes if your network size increases. So that's where several hundreds of papers are written to tackle this computational aspect. I am still in the one product case, viral marketing with one product. Yeah, this is the approximation. This is approximation algorithm. Yeah, they proved in this paper hardness algorithm. I think the hardness is 1 minus 1 by E guarantee. Yeah, this is the best actually. 1 minus 1 by is the guarantee they proved. So this is the landmark paper. If you want to study or delve deeper into this, so this is the paper you should, this is the KDD paper actually, KDD 2003. Kempe, Kleinberg, Tardas, they are the others. They from Cornell University. Actually, this is introduced in 2001 KDD paper, but they haven't defined any greedy algorithm. They introduced this influence maximization problem, the top keynotes problem, and they gave some heuristic and things like that using hidden Markov models and so on and so forth. Starting this KDD 2003 paper, KKT paper, formally defined this problem and they showed that it's computationally hard problem, and they gave this greedy algorithm. And this is like approximation algorithm which runs in polynomial time, but they did not worry about the actual computational things for real world social networks where n and m are potentially very high. Even for moderate size graphs with 100 some thousand nodes and a few thousands of edges, it suffers. You just run, you can take any this thing and just implement this quickly. I am sure some packages would be there actually. You just run this, you will understand, you will be stuck. So lot of other papers are published to tackle this computational aspect. They proposed heuristics without guarantees and approximation algorithms with guarantees in some special cases. All kinds of directions this research has exploded. Let me use that word actually. Even now it is active area. It is defined 20 years, still active area. Okay, so there are so many variants of this problem available. Yeah, I think some important references I gave. These are all like bit old references. As part of my PhD thesis, I worked on this, but of late I am not exactly working on this. But you just type in Google, search for this influence maximization through social networks, you get tons of papers. Yeah, so we also modeled this as like a game theoretic problem, because end of the day you have to select a subset of individuals, right? And we defined a cooperative game. If you recall the proposal I put forwarded on the table in the end, at the end of last presentation, the cooperative game theoretic framework. So we applied that framework to tackle this problem, and we defined something called spin algorithm. And this is, it's like a MCMC based algorithm, sampling based algorithm. It works really well, and I don't want to get into the details. So this is the computational complexity. The standard approximation is KNRM. So you can see, right, none of these terms have all those 4 variables here. So that's where we gain in terms of the computational complexity here. And we thoroughly did experimentation and so on and so forth. So visualizations also in some network, the top k nodes selected by our algorithm, if you see, they are well spread. We also like considered the how well these top k nodes cover the network. If you take only the top k nodes without worrying about the fairness things, what will happen is some of these top k nodes can be clustered among themselves. Actually, it's a network science related notion wherein highly central nodes can have like a high tendency to get clustered with each other. This is like very prominent with degree centrality. If you take top k nodes having highest degree centrality, with high chance they tend to get connected with each other. Right? In general, this philosophy holds good even if you replace degree centrality with some other notion. Highly central nodes tend to be connected with each other with high probability. We don't want that, right? Because if all the influential nodes are cluttered together, clustered together at one place, or a small number of small region of the entire network, the information spread will be like not that much, number one. I mean, they try to help actually, that's fine, but fairness point of view, it is not fair, because you may end up not touching some portion of the network at all. So fairness point of view, it is not good actually. So you have to select these k nodes in such a way that you try to cover the network as much as possible. So we, in our solution, we try to consider that fact into consideration. That's where you see the red nodes are the ones we selected using our spin algorithm. Visually also you can observe that they're all like spread across the network. This is our 2011 paper, journal paper actually. So it's reasonably well cited because at that time ours is the first work which modeled this problem as a game theoretic problem by taking into account the synergy effect, right? That's where they liked this approach very well, and it got a lot of attention. So here is another small size network, authorship network of others who are publishing in NeurIPS or NIPS conference, which is like a very flagship AI conference, AML conference. So authorship network, as you can see, the dark nodes are the top K nodes, right? They're all like well spread in the network like this. Yeah, we worked with random graphs, and so this is our proposed algorithm. This is the KKT very much baseline, and there is one 2007 paper which has improved KKT algorithm, and we compared with all these both these prime baselines for different K values. So top 10 nodes you are supposed to choose, top 20 nodes, top 50 nodes you are supposed to choose. So what happened? So the running time. So our running time is way lesser compared to KKT is like, I mean, it significantly suffers, and LKS is much better. So our speed up over KKT is like several folds higher. Okay, so far I have been like covering the foundational aspects of viral marketing with single product, right? But in real life, it is not the only scenario. There are so many interesting scenarios that can happen. Some of them are like mentioned here. So viral marketing with both positive and negative opinions. So in the scenario that I covered, we are trying to model only the positive aspects. But in real life, when individuals try out a product, they may get not only the positive opinions about that product, some negative opinions also they can develop, right? If it is a negative opinion and it's a detrimental to the product adoption thing, right? I say that, oh, please don't buy this thing, I am suffering after buying. It just spoils the situation. So you should take into account not only positive opinions spreading through the network, but also negative opinions spreading through the network. So which is like more realistic scenario. Viral marketing with competing companies. So in the first scenario, I'm just considering only one company, but the network of potential customers, if you consider, I mean, in the market, there may be like products coming, being introduced from multiple companies, right? Chat, messengers or chat applications, if you consider, there are so many chat applications you can use, not just only one particular chat application, right? And any broadband connection or any telephone network, there are so many options, but which one for me is the most important, right? That depends on my own preference to these available network options as well as my friends' recommendations. Somebody may say that, oh, this particular network I'm really feeling good, call never drops, and the data connection is amazing. On the other hand, some of my other friends might say that, oh, okay, this other network, oh, while no call drop happens, data suffers. Then why would I consider? Usually, I think that if many of my friends say that, oh, there's some issue with a particular network connection, better I don't go for that actually, right? So like that. So it's not only positive opinions, but also negative opinions also matter. That's one thing. And products from competing companies might be available. So, right, selecting influential nodes should be cognizant about this fact. Viral marketing with multiple independent products and cross-sell of products. Suppose I am a company, I am introducing, let's say, 2 or 3 new products, but there might be some dependencies among these products. How do I take into account? For example, computer and printer. I am introducing a new computer and a new printer into the market. So how I select the top K influential nodes? I don't need to select K nodes for computers and K influential nodes for printers. I don't need to do that actually. I can select, let's say, some 10 influential people for promoting my computer, and for a printer only 3 are sufficient. I'm just giving some numbers actually. So K1 and K2, where K1 can be K2 ideally. K1 need not be K2 because there is a cross-sell dependency between computers and printers. If somebody buys a computer, there is some non-zero probability that that person can buy a printer, right? So without buying a computer, what is the use of having a printer in hand, right? It doesn't make any sense. So that is what is the cross-sell thing. So if at all any cross-sell relationship among products exist, right, then the choice of influential nodes for those products should be selected carefully. So if your budget supports to target K individuals, you don't need to target K by 2 for computers and K by 2 for printers. It's a suboptimal solution. Target more individuals greater than K by 2 for computers, and for printers target less than K by 2. So call them K1 and K2. So together K1 plus K2 is your K, but K1 is usually, can be very, very higher than K2. That's what it is. Why? Because there is, clearly that there is some cross-sell relationship between the two products, like computers and printers. So, yeah, I think here are some differences. So you can, if you are interested in these kind of things, please look at that. I'm not going to cover these things in this presentation. And even product cross-sell, I myself have worked in this area. So ours is like one of the initial works in this particular aspect, product cross-sell scenario. If more than one product is targeted, at least 2 in other words, and these products are related to each other via some cross-sell relationships, how do you effectively select the influential nodes for each product in that this thing actually. We have extended the linear thresholds model for this setting, and yeah, you can look at that paper. So now what I'll do is in the next 2 slides, I'll try to cover a few very, very important latest developments, and then I will leave it, okay, for your further explorations. So the papers that I'm going to cover in the next 2 slides may target only the network aspect or network plus game theory aspect, right? Any one of these 2. So let me get started. So the first one, if you see, it's 2023 paper. So what it is doing is fair influence maximization in large scale social networks based on attribute aware reverse influence sampling. That is the name of that paper. It appeared in JAIR, Journal of Artificial Intelligence Research. This is one of the top notch journals for AIML conferences, AIML type of works. So what it does is conventional influence maximization algorithms cause unfair influence spread among different groups in the population. I just mentioned this, right, in one of our my PhD work, the spin algorithm. We did take into account this fairness aspect, but we considered the individual fairness thing. Actually, that fairness aspect we did not actually consider in the modeling part, but the final post-processing aspect we considered. But here what they are saying is most of these existing algorithms don't worry about the fairness aspects, especially group fairness aspects, in the sense that in a given network, whatever the best known top K influential nodes algorithm you select and output, these are the top K nodes you should target for, right? Those top K nodes, if you mark in the network, like I have shown the visualizations of our work, spin algorithm, etc. So those top K nodes, it is possible that they omit some groups of nodes in the network without activating any of the nodes in that group actually. So we don't want that kind of thing to happen. So it's unfair for those groups of individuals, right, present in that community without getting activated, right, due to these K nodes which you select. So it's unfair thing. You should consider this. Very important. They gave some real life scenarios wherein this is like unfair. So you can think, right, from government point of view, policy restrictions and policy enforcement kind of scenarios, this is unfair actually. So from government point of view, all states are equal, right, central government point of view. So similar thing. So whenever these kind of scenarios arise, that's where the fairness, group fairness aspects come into picture. How do you tackle the same top K influential nodes problem from the standpoint of group fairness? So in other words, whatever K nodes you output as your solution for the top K nodes problem, these K nodes in expectation should activate uh, approximately equal number of nodes in every group in that network. That is the idea. In your original definitions, that each group thing you are not worried about. In expectation, maximum number of nodes they should activate. That we should change it to in expectation, maximum number of nodes per group they have to activate. That we have to modify. That's where the entire problem scenario changes. Existing algorithms don't work for this kind of scenario. In existing scenarios, the group size is what? 1. So if you make the group size as non-trivial, greater than 1, existing algorithms don't even apply to that scenario because they are not designed to tackle the group effects. So that's where you see 2023 paper. Now if you read this paper, you may find, so they might have used some particular model, linear thresholds model or independent cascade model. I haven't seen. They might have tackled this problem using thresholds model, let us say. So same problem with the independent cascade model, nobody would have done it. So if you read this paper, that can be, because if you change the underlying model, right, the way you calculate the expected influence changes. And even your entire solution also can change following that model. So, I mean, these are all like various avenues for research. That's what I'm trying to highlight. Right? So you should always keep an eye on these latest papers in a respective area that will give you enough signals to consider newer research problems. Okay, so let me go to the next one. This is like ACM transactions on knowledge discovery. I think year I did not put here. I think this is 2022 or 2023, one of those two. So from what is this survey on influence maximization from an ML based combinatorial optimization. This is 2023 paper indeed. I forgot to put that actually. So what they are doing is from an ML based combinatorial optimization point of view. See these existing influence, what their main message is, the existing influence maximization algorithms are defined. If you go back and see that KKT greedy algorithm, right? The focus is in every iteration, the focus is a single node, right? The focus is a single node. If you select some k nodes in the next iteration, along with the k nodes, what would be the k plus 1th node? That calculation you are doing. You are fixing the k nodes which are selected, and only k plus 1th node out of among so many available unselected nodes, you are picking and keeping it here and see for which node. If I keep here, overall the expected influence is maximum, you are adding and selecting that node. So the analysis is per node basis. What they are saying is, don't do this kind of thing. This is like, of course, it's an approximation algorithm, agreed. But they are saying that don't do this per node based approximation algorithm computation. Don't even consider this route. They are saying that consider sets of nodes. They want to capture the, in a sense, they did not tell that explicitly, but their target is exactly the subset in the synergy effect they want to capture. That's where they want to tackle this problem as subsets only. Suppose if my question is to select top k nodes, if there are n nodes in the network, n ck possibilities are there. Out of these n ck possibilities, which is the right ideal possibility to output, right? So they want to tackle that as that combinatorial problem, not like this greedy algorithms wherein they add one by one node and try to tackle the problem. They say that it's suboptimal actually. Okay, that is this paper. Very, very interesting paper actually. So even I did not read, I just scanned through the initial pages. So sounds very interesting actually. So if you understand this paper, right, this opens up altogether a new way of tackling this problem. Again, viral marketing with one product with positive, negatives, viral marketing with multiple products, with cross relationships, everything you can reconsider from combinatorial optimization perspective. Again, a huge bunch of new research problems. So this paper actually. So this is Sigma 2022, computing the Shapley value of facts in query answering. Okay, so why I mentioned this particular paper is this is about use of Shapley values, Shapley value concept in a network setting. So the setting is like this. So you have some, it's altogether a new concept, new application domain. So you have, I think, how many of you have computer science background? Looks many of you. So you might have studied database management systems, right? So you have backend tables schema, and to extract information from the backend tables, you write SQL queries, right? So so you write SQL queries. The output of SQL query is some rows or some columns from some tables and so on. Now the question is explainability of SQL output. So you have some tables schema which contains data, and you have an SQL query here which outputs some records or some columns from some tables. Explainability of this problem asks why this particular output you generated for a particular question given this schema. You have to explain it, right? Explain, otherwise, see, I'll ask how many students took both game theory and discrete maths. I have the school information, students, their enrollment data, which students took what courses, all that I stored as a database schema. So some tables are there. Now my question is, how many students took both discrete maths and game theory in the last 2 years? I can write an SQL query. The output can be some 24. I am just giving an example. As an user, I get an answer 24. What is that? What 24 means? So how can I validate? Why not 36? So you should tell that, oh, okay, these are the names of 24 people who took like this. You provide a summary of that actually. Then I said, oh, okay. So 25th person is not there because there is no such person who took both these. So you have to provide explanation to that. Otherwise, just merely showing 24 is the output, why not 36? Right? So that is what is the context. Explaining the SQL query outputs is the problem. So that they tackled using, so far I am explaining the problem domain only, but to tackle this, right, they find something called provenance graphs. So taking each record or each line in the output, they try to see what is the influence of each of the input records. So they construct something called provenance graphs. So it's like a graph thing only, nodes and edges and things like that. It's a different thing, I don't want to get into that, but this jargon you can try to capture. So for every token in the output, they construct something called provenance graphs, and these provenance graphs they use to calculate the influence of input records over the output records. That's where they use the Shapley value. So very recently, Sigmod and VLDB are the top-notch conferences in database management systems area. So these kind of papers are getting published. They are modeling the relationship of the influence of the input tuples in the tables over the output generated via provenance graphs, and they calculate Shapley values of the nodes in that provenance graphs to finally generate the explanation, saying that why this 24, why not 36, that kind of thing. Okay, so this is like an emerging area. It uses both networks, right, graphs or networks, and game theoretic solution concepts. So coming to the next one, graph game embeddings. This is AAA 2021 paper. So what it does is, so in game theory, so we just briefly looked at the cooperative game theory notion. So there is also the other branch called non-cooperative game theory notion. So in it's just like when you play some game, chess, right? So it's a two-player game. Every person has a lot of strategies, right? Several strategies at his or her disposal. Given the other player's move, so our set of strategies might be limited. Among those limited set of strategies, which is the best move, I decide, and then accordingly, execute my move. Then in the next iteration, given my move, my opponent, given the limited set of strategies that he has, given this condition, he or she will take the best move. So like this iterative process continues. So the strategies part I'm talking, right? Every person or player in case of chess, they have strategies. So whether I should move this to here or there, that is called strategy. So in general, they capture using non-cooperative game theoretic notion. So players would be there, and every player has some strategies. If I take one particular strategy, what is my utility, right? Whether I am going to win or going to lose or something like that. So you have players, you have strategies, you have utility functions. Together will define a non-cooperative game. They try to construct a graph using the strategies of the players, and using that graph they try to calculate the embeddings of the graphs, and using those embeddings they try to calculate the outcome of that game. In a non-cooperative game, the outcome is defined by so-called Nash equilibrium outcomes actually. So they are trying to correlate the graph notions and the embeddings calculated using those graphs to game theoretic notions actually. So it's a like very interesting thing, if at all you are interested in this kind of direction. And yet one more interesting paper is the graph structure of two-player games. This is like 2023 paper. It is also like somehow constructs a graph out of a game setting and leverages that graph to solve the game problem. So again, it is like a good combination of networks plus game theory concepts. So I thought of like highlighting some of these things which cover both graph part and game theory concepts, or only graph part or only game theory concepts, so that by no means this is a exhaustive list, right? So these are just sample 4 or 5 papers which I felt are like most interesting and important. I am just highlighting. I think, yeah.